Hello, dear viewers. We are continuing where we left off with scaling in theoretical physics and its application to neural activity and consciousness. It is intended to bridge the gap between general relativity, GR, and the concept of consciousness by using theoretical frameworks such as the ADS-CFT, anti-de Sitter conformal field theory, correspondence to draw parallels between the effects of gravity in spacetime and the emergent properties of consciousness in the connectome of the brain. It is suggested that the structure and activity within the neural networks of the brain can be likened to the fabric of spacetime, with consciousness acting as an analog to gravity. Both are emergent properties resulting from complex, coherent interactions across dimensions. Let's begin by discussing the self-referential nature of the gravitational field in GR, where the curvature of spacetime simultaneously shapes and dictates the behavior of the mass energy within it. This concept, expressed by physicist John Wheeler, supports the parallelism between gravitational interactions and neural processes. In the proposed analogy, the brain's neural pathways and synaptic interactions form a kind of connectome spacetime in which the geometry of this connectome influences the flow of neural signals, just as the geometry of spacetime influences the trajectories of masses and light in the GR. Here, action potentials representing neural firing patterns are seen as following geodesics within the four-dimensional structure of the connectome. Extending this analogy, we can suppose that consciousness serves as the brain's gravitational field. This is a provocative and abstract concept, positing consciousness not as a byproduct of neural activity, but as an intrinsic property of the geometry of the connectome, a curve of the brain's spacetime in response to coherent neural activity. Neural activity, represented by a tensor similar to the energy-momentum tensor in the GR, curves the space of the connectome. As a result, consciousness emerges as a product of a geometric structure that is inseparable from the topology of neural connections. The ADS-CFT correspondence provides a framework for understanding how gravity in a higher dimensional 5D bulk spacetime can be mathematically equivalent or dual to a quantum field theory in a lower dimensional 4D boundary. Proposed by Juan Maldacena in 1998, this duality has profound implications in theoretical physics, particularly in the ongoing search for a quantum theory of gravity. According to this model, the dynamics of gravity in a 5D curved spacetime are mirrored by a gravity-free 4D quantum theory in the boundary. This holographic interpretation is strikingly relevant to the brain connectome analogy and suggests that consciousness may be a manifestation of neural interactions projected into a similarly higher dimensional framework. For the brain, the 4D boundary represents the complex structure of neural networks within the cortex, while the 5D mass encompasses the emergent phenomenon of consciousness. Just as gravity is not present in the fifth dimension but emerges from it, consciousness is not defined as a true fifth dimension, but rather as a higher-level emergence from coherent neural activity at the level of the cortex. In this context, the holographic principle is utilized by likening consciousness to a three-dimensional holographic image projected from a two-dimensional surface, where the third dimension of depth is an illusory byproduct of interference patterns in coherent light. Similarly, consciousness is envisioned as a 5D structure resulting from the interference or interconnectedness of neural events within the 4D cortical network. The holographic framework therefore presents a dual, five-dimensional model of consciousness. Rather than viewing consciousness as a byproduct of brain activity, this approach suggests that it is a fundamental property encoded within the structure of the connectome. He proposes that the apparent duality between consciousness and matter can be reconciled by framing the brain's connectome as a five-dimensional structure. In this model, the fifth dimension allows for the emergence of an immaterial, private consciousness as a binary counterpart to the material, public functions of the four-dimensional cerebral cortex. This perspective implies that understanding consciousness may require exploring the 5D connectivity space-time, potentially leading to new approaches to neuroimaging and data interpretation that combine physical brain activity with subjective experience. In visualizing this concept, the framework utilizes the ADS-CFT correspondence to represent consciousness in a binary structure. On the ADS brain side, a circular concave space representing the higher dimensional anti-de Sitter space is filled with intricate, tortuous neural pathways symbolizing the complex structure of connectivity. This space is contrasted with a CFT/brain side depicting a flat, lower dimensional plane with simpler neural connections. Among these representations, mathematical symbols such as Einstein's field equations and stress-energy tensors are transformed into correlators and operators on the CFT side, indicating duality. Entropic measurements also indicate the curvature of the ADS field and the complexity of the neural network, and holographic projection lines show the mapping of neural connections onto the 2D boundary. At the heart of this holographic model is the emergence of consciousness, visually represented by a glowing aura from the core of the connectome, symbolizing consciousness as a holographic effect influenced by both the complex mass, connectome, and the flat boundary, CFT. By applying the ADS-CFT framework to neuroscience, this speculative model suggests a way to understand consciousness as an intrinsic part of brain structure, potentially reshaping neuroimaging and the interpretation of neural data. It proposes that the 4D neural pathways of the physical brain serve as a boundary where the mind emerges in a higher dimensional sense, connecting the physical with the experiential. This raises profound questions. If consciousness is simply curvature, then might understanding consciousness be tantamount to understanding the neural geometry of the brain rather than finding a particular field or substance responsible for it? However, this perspective also raises theoretical difficulties. In GR, curvature arises from well-defined mass-energy sources, and interactions are governed by Einstein field equations. There is no established equivalent to Einstein's equations for the brain that rigorously connects neural topology with conscious experience. The curvature consciousness connection is based on analogy rather than on an established neural field theory that can be mathematically formalized. Another intriguing implication arises from the fact that, under the ADS-CFT framework, gravity itself has no unique or intrinsic cause. It is simply a property of the binary relationship between dimensions. This view sidesteps the need to define the origin of gravity by reinterpreting it as a phenomenon that emerges in a binary space. Extended, the idea that consciousness emerges and lacks an underlying essence may suggest that consciousness, like gravity, can never be fully explained in traditional terms. Instead, it may be a result of complex neural interactions structured across dimensions and may evade direct reduction to simpler processes. This interpretation remains theoretical and primarily serves as a conceptual bridge between neuroscience and fundamental physics. Although these insights do not provide an empirical solution to questions about consciousness, they do provide a new framework that can stimulate further interdisciplinary research. Such discoveries, if approached with caution, could lead to new models in which the geometric and topological properties of neural networks are considered intrinsic to understanding consciousness, even if the precise nature of this relationship remains fundamentally complex and elusive. The proposed framework suggests that consciousness can be quantified by measuring the curvature of the connectome in functional space-time, aligning this metric with the levels of neural connectivity in the brain. Empirical evidence supports this approach. When brain connectivity density decreases, as observed during deep sleep or in patients with disorders of consciousness, e.g., minimally conscious or vegetative states, consciousness appears to decrease. In such cases, the brain may still exhibit localized cortical responses to stimuli, but it lacks sufficient small-scale, proximal connections to support the kind of integrated, global curvature that gives rise to consciousness. This suggests that measuring functional connectivity curvature could serve as an objective marker of consciousness, transforming consciousness from a vague subjective experience to a quantifiable state. Quantifying this curvature could be valuable in assessing various states of consciousness. For example, brain imaging can track changes in functional connectivity, providing insights into patients' fluctuating levels of consciousness over time. For example, depression presents a distinct pattern. Neuroimaging reveals increased connectivity within the pre-default network and the salience network, which correlates with patients' subjective experiences of slowness and heaviness. Here, increased short-range connectivity translates into an overall reduction in signal propagation speed, which translates into a physiological experience of slowness, a link between the connectivity architecture and the perceived temporal experience. In contrast, the intense, widespread disconnection seen in psilocybin-induced desynchronization, particularly within the default mode network, corresponds to the acute changes in space-time perception characteristic of psychedelic experiences, suggesting a fundamental link between the connectome landscape and the nature of consciousness. Furthermore, this framework implies that consciousness requires a certain latency period for manifestation, as incoming sensory events must reshape the 4D landscape of connectivity to reach conscious awareness. Subliminal stimuli that are briefly presented and then masked provide an example of environmental information that can enter the cortex but fail to reach conscious recognition, suggesting that rapid events may fail to warp the connectome landscape sufficiently for awareness. This effect is also evident in psychotic disorders, where disruptions in white matter integrity may prolong the time required for stimuli to enter conscious processing. Extending this view, mental disorders themselves can be viewed as manifestations of an altered connectome spacetime, with each disorder representing a unique pattern of connectivity-based spacetime geometry. This perspective even provides new insight into the long-standing debate about free will. Functional MRI studies have shown that decision-related neural processes begin long before conscious awareness, raising the question of whether conscious choice is merely an epiphenomenon, a product of earlier connectome activity outside the conscious realm. Thus, the freedom we experience in decision-making may simply be an artifact that emerges after the fluctuating landscape of the connectome has shaped an action trajectory that we then interpret as a conscious choice. In this framework, awareness of any particular event is not instantaneous, but results from a time-consuming reshaping of the 4D connectome spacetime. This reshaping, which occurs beyond the immediate reach of conscious perception, forms the basis for conscious experience. Consciousness is thus only the visible part of a vast underlying process of connectome curvature, and awareness at one moment represents the culmination of a long series of fluctuations in the neural landscape. This tip of the iceberg view suggests that consciousness is only a portion of the brain's larger, ever-fluctuating connectome dynamics, much of which occurs outside of conscious access. This speculative framework takes a holographic approach to consciousness, positing that an idea entering the mind represents a shift in the space-time geometry of the connectome. In this view, the brain's connectome, mapped as a four-dimensional network, experiences a moment of functional curvature as conscious thoughts or experiences traverse the structure. It is analogous to bending a two-dimensional plane into a higher dimensional form. This curvature occurs as neural activity spreads across interconnected cortical regions, representing ideas or thoughts as entities existing in a 3+1 dimensional space. Here, the process of manifesting an idea is framed as a transformation in spacetime dimensions, consistent with the complex, higher-dimensional interactions proposed in theoretical physics models. During paradoxical REM sleep, when cortical activity increases and dreaming occurs, the frame has been proposed that the connectome reaches a singular, conscious state, even when external sensory inputs are largely ineffective. This highly connected state within the cortex gives rise to spontaneous associations and pseudo-randomness in perceived space-time, shaping the surreal experiences characteristic of dreams. Interestingly, this concept aligns with the idea that the curvature of the connectome intensifies during REM sleep, enabling the establishment of connections between spontaneous internal events, potentially reviving or recombining previous experiences into dream narratives. This warping of higher dimensional spacetime during dreaming can affect the structural or functional patterns of the connectome, leaving memory traces that can solidify or change network content. Extending this model of consciousness to a higher dimensional warping opens up intriguing parallels with AI. While AI relies on large data sets processed by algorithms, it operates without the same inherent capacity to generate spontaneous thoughts seen in human creativity. For example, Einstein's theories of relativity emerged from deep introspection and conceptualization, independent of large pre-existing data sets. In contrast to this intuitive process, the generative capabilities of an AI are externally induced and lack the spontaneous, self-referential quality that characterizes human cognition. This external stimulation highlights an important distinction. While AI can handle advanced conceptual manipulations, such as generating theoretical images that mimic aspects of the ADS-CFT correspondence for brain models, it does not generate these ideas from internal processes. In essence, the consciousness of AI is a reflection of human mental processes that rely on users to initiate or bend its algorithmic operations. Thanks for listening and take care.